something new today. We're trying Mr. Agnew at the chalkboard, recording a lesson. Now, the reason why this chalkboard is so short is this is not, in fact, a chalkboard. This is a chalkboard table that my daughter loves to draw on that I've turned up on its side. This is the IKEA hack I am proudest of. And yes, that's a little hole right there. That's where you sweep the sweepings when you cleaned up your chalkboard. So this is not a perfect setup, but we're going to make do. The purpose of this lesson is to cover the basic level of logarithms that you will need for this class. You covered a lot more logarithms than this back in Algebra 2. We are not going to review every bit of logarithms you've covered in Algebra 2. We're just going to cover the most fundamental basic level that you will need to solve the sorts of problems that come up in this class. So our little agenda, number 1, what the heck is a logarithm? Number 2, a little bit of practice with those logarithms. Number 3, using logarithms to solve equations that will come up. And that brings us to how do you do logarithms on your calculator. So first of all, number 1, what the heck is a logarithm? So back in Algebra 1, you would solve an equation like y equals 2 times x. You said, great, the opposite of multiplication is division. Divide by 2, and I get that y divided by 2 is x. Or you'd see something like y equals 2 plus x. Okay, what's the opposite of addition? Subtraction. Minus 2, y minus 2 equals x. Or even you might see something like y equals x to the power 2. What's the opposite of squaring? Square rooting. Square root both sides, plus or minus square root of y equals x. So this idea that to get rid of an operation, you do the opposite of it to both sides, and instead of y equals x squared, you have x equals square root of y, because square and square root are somehow opposites. Technically, they're called inverses. But then you get to Algebra 2, you learn about exponential functions, and you get as far as y equals 2 to the power x. Then you say, okay, what's the inverse of 2 to the power x? What do I do to both sides to get the x out of that exponent? And you realize you don't have an operation. There is nothing you've learned up until that point that will actually get that x out of the exponent. So that brings us to logarithms, which are a completely artificial, made-up operation. A bunch of dorks in their nerderies got together and geeked out for a while and came up with this operation whose sole purpose is to get that x out of the exponent. In much the same way, if you think about it, that the sole purpose of a square root is to undo a square. A square root is not an operation you come across in nature. This is not a normal thing we see. It's a really artificial operation whose purpose is to be the opposite of squaring. Logarithms are the same idea. Their purpose is to be the opposite of exponents, or the inverse, to be technical, of exponents. And the way we rewrite this logarithmically is we write the log base, and then whatever the base of the exponent is, that becomes the base of the logarithm, and we write it down here like a little subscript. And then there's the x and the y. The x used to be paired with the 2, and the y used to be by itself, and we're going to switch that. The x is now paired with the x is now by itself, and the y is now paired with the 2. So these two equations are equivalent in the same way that these two equations, or I should say, in the same way that these two equations are equivalent, in the same way that y equals x squared is the same as x equals root y. Those are the same equation expressed the same way. If y is 4 and x is 2, these both work. 4 equals 2 squared. The square root of 4 equals 2. This works for both cases. The same way here, if x is 3 and y is 8, these are both true. 2 to the third power equals 8. The log base 2 of 8 equals x. So that's what a logarithm is. It's the inverse of an exponential function. That takes care of step 1. Now let's move on to a little bit of practice with logarithms. First, let's just practice writing them in and out of logarithmic form. So let's say I've got something like 4 to the third equals 64. True story. If I want to rewrite that as a logarithm, that's then the log base 4, and then the 3 and the 64 switch positions. The 64 now goes with the 4. The 3 goes by itself. The log base 4 of 64 equals 3. Here's how to think about log base 4 of 64. It's like a question. It's like asking 4 to what power gives you 64? 3, because 4 to the third power is 64. Let's do another one. Let's put the exponent on the other side so we practice with that a little bit. Let's say I've got 9 equals 27 to the 2/3. There's a blast from the past. Remember, when I raise it to the power of a fraction, this is like take the cube root of 27, which is 3, and square it, which is 9. So this is a true statement. So I'd write the log base. The 27 was the base of the exponent. It now becomes the base of the logarithm. The 2/3 and the 9 switch positions. The 2/3 used to be with the 9. Now it's by itself over here. The 9 used to be by itself. Now it goes here. And there I've rewritten this as a logarithm. Let's do a little bit more practice. What if I just give you a logarithm and ask you to evaluate it? And we'll keep these relatively simple. Let's say I've got the log base 5 of 25. What is that equal to? I'm going to do the Daniel Tiger thing where I pause long enough to give you about time to get half an answer out. What is that equal to? Good, yes. That's equal to 2, because 5 to what power is 25? 5 to the 2 power is 25. So there we go. Let's say I've got something like the log base 2 of 16. What's that equal to? Good, 4, because 2 to the 4 power is 16. This is like saying 2 to what power is 16? And the answer is, of course, 4. Sometimes you might get one that's a little bit more complicated that you have to kind of untangle to think about. Let's say I had the log base 1/2 of 32. 1/2 to what power is 32? So in that case, I might actually reverse this process a bit. I might say, hey, let's pretend it had said equals x. Let's just pretend. Then to rewrite this exponentially, good practice, the base stays the base. The number that used to be paired with it is now by itself. The number that used to be by itself is now over here. Doesn't necessarily get us there. I can take this a step farther. 1/2 is like 2 to the power -1. 32 is like 2 to the power 5. And there was an x there. X has got to be -5 because -1 times -5 is 5. So that's the answer to that logarithm. 1/2 to the -5 equals 32. The log base 1/2 of 32. The log base 1/2 of 32 is -5. The negative changes the 1/2 to a 2. And the power 5 gets us to 32. So there's a little bit of practice playing around with logarithms. Now let's take an example where logarithms are actually going to come up. We're actually going to have to solve. Let's start with a really simple example, then move on to a more complicated one that better represents the homework that you're actually going to see. So a really simple example is going to be 500 equals 3.4 to the x. I want to solve for x. Well, to get the x out of the exponent, I'm going to rewrite this logarithmically. I'm going to write the log. The base stays the base. These two numbers switch positions. The number that was by itself is now in the logarithm. The number that was, the letter, the x that was paired with a 3.4 is now by itself. So my answer is log base 3.4 of 500. How do we evaluate that? We'll get to that in a second with the calculator. In other words, 3.4 to what power is 500? I know 3 to the 4th power is 81. 3 to the 5th power is 243. This is a little bit bigger than 3, so I'm going to guess my answer is somewhere around 5 or 6. 3.4 to the 5th, 5 point something power is probably going to give me 500. That's my guess, somewhere around 5 or 6. But let's write that down here so we can come back to it and get to the calculator. Log base 3.4 of 500. I bet you guys have all missed my terrible handwriting, huh? Not. Okay, let's do another one that's a little bit more complicated, like something you might actually see on the homework. Let's say we're graphing COVID-19 cases. And I have a certain city where I start with an initial set of 200 cases. I wrote a 300 cases. And they're growing at a rate of 30% per day, which is about right for some environments. First, let me write that as an exponential equation. Remember, exponential equation is of the form y equals a times b to the x. The a is the y-intercept. It's what you get when x is 0. And in this case, we said that's 300 at day 0. There are 300 cases at whatever day we're starting the clock. And then b is what's called the growth factor. That 30% is my growth rate, which I need to write as a decimal. That's going to be 0.3. To change it from a percent to a decimal, that's 0.3. But that's not b, that's r. Remember, b equals r plus 1. 1 plus 0.3 is 1.3. So this is the equation for how many people have coronavirus, assuming that you started with 300 and it's growing at a rate of 30% per day. All right, so let's say I want to know, all right, when do we hit 10,000 cases? When do 10,000 people have coronavirus? Got to get rid of that 300. Cancel a couple of zeros. That's 100 divided by 3, or 33.33. Equals 1.3 to the x power. And then lastly, I need to get that x out of the exponent, so I'm going to rewrite that logarithmically. X equals the log base 1.3 of 33.33. How do we evaluate that on our calculator? So now we have two things to evaluate on our calculator. So that takes us through solving. And let's lastly hit evaluating on your calculator.